What are some of the advanced engine classifications? Some of the engine classifications that primarily we saw are based on fuels, the number of strokes, and so on, right? Now, if you go for certain advanced classification, you can go with number of cylinders. It can be single cylinder or two cylinder, four cylinder, eight cylinder, six cylinder, even up to 12 cylinders. There can be even large number of cylinders. And then classification of engine can be based on arrangement of these cylinders. How are they arranged? Are they arranged in line, one after the other, in a row? Or are they arranged in a V shape, right? Or are they arranged vertically opposed or horizontally opposed or in a rotary manner? There are several different arrangement of cylinders that are possible, right? So based on that also you can classify engine. Then arrangement of valves and valve trains. How they, depending on how you are having the number of cylinders, valves and valve trains will also be arranged accordingly. So based on that also you can classify the uh, engine. Then of course type of cooling. You have two types. One is air cooled engine, another one is liquid cooled engine. Then based on number of strokes per cycle, that we discussed already, whether it is two stroke or four stroke. And then you have type of fuel burned, right? That also we discussed already, whether it's diesel or petrol, or there can be CNG or several other types of fuels that may be used. So method of ignition, again, whether it is compression ignition or spark ignition, right? So either of the cases we can consider. Just give me a minute. I have something small. Yeah, sorry for that short interruption. I had something to do, so I had to just get it done. Is my screen visible now?
Yes, yes, visible.
Yeah. Yeah. So, based on the type of fuel burned, we discussed, based on method of ignition, you can either classify them as compression ignition or spark ignition. And then there is something called as firing order. Because when you have multiple cylinders in an engine, which cylinder is fired in which order? You may number the cylinders as one, two, three, four, one after the other. But then the way you fire them, whether first cylinder is getting fired first and then second and third and fourth, or one, three, two, and four, or one, four, two, and three, there are different methods in which you can fire the cylinder. Why do we do that? The reason is to ensure there is power balance, right? Because if you go in a sequence one, two, three, four, the impulses on the crankshaft will be just one sided and it will be from one side to the other. We don't want that. There will be severe bending forces acting on the crankshaft. So we want the impulses to occur at different locations on the crankshaft, such a way that the crankshaft is also properly balanced in power impulses. So in that way, firing order will vary depending on number of cylinders, depending on number of the type of arrangement. Firing order will also vary. So for that, again based on that, engines can be classified. And then, of course, you can have reciprocating engine or rotary engine. We are not going to discuss any rotary engines, Wankel engine and other different engines are there. But generally, what we discuss are reciprocating engines. All right. So this is how we have advanced classification of engine. I'll just show you some pictures. Before that, number of cylinders you can have a row of cylinder in line or two rows V type, two rows horizontally opposed you can have, or you can have radial, like spokes on a wheel, radial type, right? So you can see typically these are, yeah, this is inline engine, inline four cylinder engine. This is two cylinder V type, and this is horizontally opposed four cylinder engine. Two cylinders are on the top. I mean, horizontal or vertical. This is what is shown here is vertical. If you just flip it, it is horizontal. Usually, horizontally opposed engines are preferred because balancing is better in the horizontally opposed engine rather than a vertically opposed engine. I mean, vertically opposed engines are way more balanced than inline engines. But even compared to vertical, horizontally opposed engines are better, considering the gravitational effects and so on. Now, what you have is a radial type engine, different cylinders having power stroke in different timings, and then you have the whole crankshaft rotating in the center. So you can have much better balancing in a radial type, but then there is enormous complexity in terms of construction because the valve arrangement, the camshaft arrangement, and all those things become very, very complicated in such a radial arrangement. The arrangement of valves and valve trains, the location of the crankshaft, I mean camshaft, I'm sorry. You have a camshaft which, have you designed cam profiles in kinematics of machinery or kinematics? Have you designed cam profiles?
Yes, sir.
You have designed cam profiles, right? Yeah. So for a certain period of time, the valve should be kept down, and for a certain period of time, the valve should move down, and then for a certain period of time, it should go up. So you have cam profile, and based on the profile, the cam has to be made, and then there's the cam shaft, right? The axis is offset. The cam is not axially located. There is an offset in the axis, so the cam can operate the valves. So the camshaft may be located in the cylinder block or on the cylinder head. So you can have different locations of the camshaft. And how the camshaft is driven, whether you have timing gears or sprocket and time chain or sprockets and two timing belt. So different ways you can operate the camshaft. Based on that also engines are classified. The type of valve train, whether it is overhead camshaft or camshaft and block or overhead valve. I'm sure in prime movers, when you were discussing engines, you must have looked at how the cam and how the valve is operated, whether the cam is directly on the top or there is a push rod and whether the valve is operated. So based on that also, you have different classifications. The number of valves per cylinder. You can have more than one inlet valve and more than one exhaust valves. There can be two, three, four, or even six, depending on how quickly you want to, or how much charge and what kind of distribution you want inside the cylinder. You can have multiple valves, multiple inlet and multiple exhaust valves. As long as the timings are appropriately maintained, you can have multiple valves per cylinder, right? So that is also another advanced engine classification. So type of cooling, you can have either air cooled or liquid cooled. Then if you go by the firing order, we have sequence in which cylinders deliver the power strokes. So for inline four-cylinder engine, the general firing order is like this: 1, 3, 4, and 2, or 1, 2, 4, and 3. It's never 1, 2, 3, 4. It will never be in that order because you will have uh, power impulses imbalance on the crankshaft, right? Reciprocating or rotary engine, as I said, gas turbine engines and Wankel engine, these are rotary engines. Gas turbine engines are mostly used in jet aircrafts and so on, where the gases rotate the turbine, right? And then you get the rotary movement. And then there is Wankel engine where the piston itself is shaped in a very different manner. Apart from that, most of the engines that we use are reciprocating type engines. Okay, I mean, you guys still remember all your formulae and so on. I just want you to solve this. Can you quickly note down this problem and solve and tell me? In an air standard Otto cycle, the compression ratio is 7 and the compression begins at 35 degrees centigrade and zero point 0.1 megapascal. The maximum temperature of the cycle is 1100 degrees centigrade. So find temperature and pressure at various points in the cycle, heat supplied per kilogram of air, work done per kg of air, and the cycle efficiency. Just a review of Otto cycle and diesel cycle. Probably we'll just solve this one problem. I would like to see whether you people remember still the formulae and the calculations involved. This is more or less goes back to thermodynamics, right? You studied this in thermodynamics? Yes or no? Did you study Otto cycle and diesel cycle in thermodynamics or you studied them in prime movers?
In thermodynamics, we have studied as well as in PMS.
Okay, so probably can solve and tell me. I go, yeah, let's say, if let's say this is how the whole thing looks like. 1 to 2 is suction, 2 to 3 is compression, 3 to 4 is constant volume heat addition, 4 to 5 is power stroke or um, adiabatic or isentropic expansion. Then 5 to 6 is constant volume heat rejection. So can someone quickly say from where to where the piston moves? 1 to 2 and then 2 to initially 1 to 2 is suction, then the piston moves from 2 to
3.
no. Is it 2 to 3? Yeah. You can say 2 to 3, correct. Then
3 to 4.
there is no movement of piston from 3 to 4, right?
3 to 5, sir.
3 to 5. So you can say it moves from 2 to 4, you can say in one sense. Actually, 3 and 4 are in the same distance because you look at the PV diagram, it's the constant volume line. So the piston is not moving beyond 3. So 3 and 4 are on the same line. So if you say the piston is moving from 2 to 3, it is essentially same as saying from 2 to 4. Only the condition of gases inside the cylinder is varying. So that is why 3 to 4 there is a line. But as far as the piston movement is concerned, the position is only 3. Then again, during expansion time, it is moving from 3 to 5, 6. 5 and 6 are again in the same location. So essentially, the piston is moving between 1 and 2 only, the top dead center and the bottom dead center. Okay? So you have to visualize that. So can someone give me some values? So T2 is given, P2 is given. So can we find P3 and T3? So we are assuming that all these, I mean, the gases are ideal. So you can use the ideal gas equation. PV is equal to RT. PV is equal to rho RT or whatever. So what's the value of P3 and T3? Has anyone found out? Someone putting it on the chat box. I don't know. Am I still connected?
Sir, T3 is somewhere about 670 kelvins.
Okay. What about V3?
V3 is 126.28 cubic meter.
Let's see. Yeah, T3 is 670 Kelvin, that's right. P3 is given. I think it's pressure and temperature. So P3 is 1524. Are you guys getting this? 1524 kilopascal. Because you know this P3 by P2 is equal to V2 by V3 power gamma. PV power gamma is constant. So from that, using the compression ratio, you can get, I think P2 is known, the ratio is known. So you can get P3 as 1524 kilopascal. This one,
Yes,
are you
sir.
guys?
1524.43 getting, sir.
Yes, it's fine. So, and then T3 by T2, again, you can use the same ratio, V2 by V3 power gamma minus 1 now. So again, I think T2 is given, right? T2 is given as 308 Kelvin. So that gives you T3 is 670.8 Kelvin. And anyway, T4 has already been given. So now we know the values of P3 and T3. P4, do we know? We don't know P4, but we know T4. So V3 and V4, we can get it. How? V3 is equal to? No. V3 is equal to V4, right?
Yeah, yes, sir.
It's a
Yes,
constant
sir.
volume process. V3 is equal to V4. It's a constant volume process. So we can simply say P3 by T3 is equal to P4 by T4. So from there you can get the value of P4. Since P3 and T3 and T4 all three are known, you can get P4. Are you guys getting 3119? Is there any difference in the values? Can someone just confirm? P4 is 3119 kilopascal, right?
Yes, sir. 3119.36 P4.
Good. So then, of course, we have 4 to 5 is isotropic expansion. Again, you can use PV power gamma as constant. So from there, we can get T5 because same we can use T5 by T4 is equal to V4 by V5 power gamma minus 1. It's the same. I mean to say, volume 3 and 4 are same. Same way, volume 2 and volume 5 are same. So from there, you can get the value of T5. What is T5? Are you guys getting 630 Kelvin or 631, whatever?
Yes, sir. 630.42 somewhere.
Yes. So we have T5 around 630. So now the heat input. So since the heat addition is happening at constant volume, we are taking Q in as CV delta T, right? CV delta T, that is CV T4 minus T3, because the heat addition is happening from 3 to 4 at constant volume. So CV delta T. And this is specific heat addition because we don't have the mass here. So the unit you get is kilojoule per kilogram. CV value is 0.718 kilojoules. The unit appropriate. So T4 is 1373 minus T3 is 670.8. What you get is 504.18 kilojoules per kilogram. So 0.718 kilojoules per Kelvin is CV value. So note we are using CV that of air, right? The same way heat rejected, you can find out CV delta T T5 minus T2. Again, that's constant volume heat rejection. So what we'll have is 231.44. So the net work obviously is Q in minus Q out. So W net is 272.74 kilojoules per kilogram. And thermal efficiency, what you get is work net by Q1, so 54% is what you get as thermal efficiency. So which you can directly calculate 1 minus 1 by R power gamma minus 1. So again you get it as 54%. Right? This is with an assumption that all the processes are happening isentropically at constant volume and so on. What do you mean by perpetual motion machine of the first kind? PMM1.
So violating first law of thermodynamics.
Yeah, tell me what it is. Sorry. It violates first law means what it does.
Without any initial input, it can generate energy.
Without any input, it will go on giving output energy. Right? That is perpetual motion machine of first kind. What is perpetual motion machine of the second kind?
All the heat is completely converted into work without any wastage.
Yes. That is also not possible. So you can't even have perpetual motion machine of second kind. So it is not just sufficient that a system, what do you call, satisfies the first law. System should also satisfy the second law. Right? System should also satisfy the second law. So sometimes you may have a system. That's why in many research work, people just don't check the first law of thermodynamics. They see that okay, whether energy conservation is there or not, that is okay. But then second law should also be satisfied. If someone says that their efficiency is 100%, again, it's questionable. You can't have it. Perpetual motion machine of second kind is just impossible. What is the maximum efficiency that you can get then? 100% is
Carnot
impossible.
efficiency.
Yeah. The highest efficiency that you can get is Carnot's efficiency. Even that is almost impossible. Why?
Sir, everywhere there are frictional losses and irreversibility.
There are irreversibilities, right? Everywhere there are irreversibilities. So you can't have the processes, all the processes reversible and adiabatic reversible process. You can't ensure them always. It's just impossible, almost impossible. That's why Carnot's efficiency is also impossible. What to talk of 100%? It's just not possible at all. Right? So the maximum you can try to achieve is Carnot's efficiency. That also only an attempt can be made. Even then, it's not so easy to achieve very high efficiency. So typically, if you look at an engine, the heat given to an engine, where it goes, so when we say 50% efficiency, it's fine. Where it goes, where the 50% efficiency means you have given where the heat input is given in the form of combustion gases into the cylinder, right? What happens to this heat? Only 54% of it is converted into work, right?
So some of it
Generally,
goes to, I mean, heating the different elements of IC engine.
yeah, generally 54% is not the typical value. It's approximately 30%, 35%. 54% is very high actually. So remaining what happens? Heating the, what did you say?
Sir, I mean, different components of IC engine, they get heated, right?
It is
Radiation losses.
not, yeah, you should say that there is loss, heat loss through the walls of the cylinder. There is heat loss through the walls of the cylinder. That is one component. What else happens? What else
Friction
happens?
power.
No, directly something happens.
Exhaust gases.
Exhaust gases, simple. There is a lot of heat loss through the exhaust also. So there are three components if you look at. One is a certain part of heat is getting converted into work through the piston crankshaft arrangement. One part is just pushed out through the exhaust, and another part is dissipated through the walls of the cylinder into different components. So to minimize that damage, only we have cooling system, right? Minimize the damage to the engine components. Just to minimize the damage to the engine components, we have the elaborate cooling arrangement. Otherwise, this 30% of heat that is getting dissipated through the cylinder walls is very huge amount of heat. You can just calculate it. Consider the calorific value of the fuel. If you find out what kind of mass of fuel is coming into the cylinder, and then the amount of energy that is released, one third of it is just getting dissipated through the walls. So the cylinder walls can completely warp, and many of the components can just melt if you don't have proper cooling system in place. So that anyway we'll discuss while we are discussing the cooling system. But I thought since the term efficiency came here, I just wanted to bring back it into perspective how um, there's always a certain limitation on the amount of heat that can be utilized for useful work, right? Yeah. There is another problem. You just note down the problem, you can solve it later on. So just note down this problem, you can solve later on. Meanwhile, just key in your attendance in the chat box. So anyone has any questions till now? I hope you have noted down. Okay. So I'll just give a brief introduction to the multi-cylinder engines. See, two balances are very important. My screen is visible, right?
Yes, sir.
Yes, sir.
Okay. Two types of balances are important for an engine. One is called mechanical balance, another one is power balance. So, mechanical balance means moving parts counterbalance in operation and minimize vibration. Power balance means power impulses occur at regular intervals and exerts the same force. So, these two are very crucial for an engine. So these are the two balances which are taken care of by a multi-cylinder engine as opposed to a single cylinder engine. How many cylinders is advantageous? What kind of arrangement is advantageous? Why so? All these things we will discuss. Okay. But then I just want to know: have you guys discussed about engine balancing in kinematics or dynamics? Balancing of rotating masses, balancing of reciprocating masses. Have you
Yes,
studied
sir.
that?
In dynamics of machinery, we learned.
In dynamics of machinery, you studied about balancing of reciprocating masses. So, what type of balancing needs to be done in reciprocating masses? Can they be totally balanced, reciprocating masses? Can you achieve total balance of reciprocating masses and rotating masses? Yes, important question. Okay, think about it. All right. So, how these balancing is done, you can just review some of the topics that you studied in dynamics. Here, we will also discuss why you need to have multiple cylinders, what type of advantages a multi cylinder engine provides for us. All right. So, that topic, we'll take it in the next lecture. Any questions?
Excuse me, sir.
Yes, Aditya.
So in the last class, you asked about the transmission system of a diesel locomotive.
Yeah. Did you find out the answer?
Yes, sir.
Oh, so tell me how the transmission was done.
Sir, actually, it's like smooth just because DC, sorry, like three-phase motor is there to like get it running,
Hmm.
and the diesel engine provides the what we can say that it is basically a generator which used to
Very
uh,
good.
drive the other thing.
Charge the battery.
Yes, sir.
It stores, diesel engine in a diesel locomotive is very important. Diesel engine in a diesel locomotive is just like a powerhouse. It's like a generator. It generates power, and you have storage, power storage, like a battery or capacitors or whatever. You have that storage elements. So power is stored, and from there, the DC power is given to the DC motor. So DC motor is what runs the locomotive. Though you have diesel engine in a diesel locomotive, the engine is no way connected directly to the wheels. That's why you have very smooth transmission. So this was very interesting. First time when I came across this information, I thought that just like steam engine, the engine is directly connected to the wheels. But if you connect the engine directly to the wheels, the kind of complex transmission system that you have to arrange is enormous arrangement. Enormous complexity is there because the kind of power that is involved. It's not that it's impossible, you can do that, but you won't get this type of control, very smooth transmission and control when it comes to diesel locomotives. So even in diesel locomotives, it is more or less like an electric locomotive. Only thing is that the electric power doesn't come from the supply lines that are running on top, but it comes locally from within the locomotive where the diesel engine runs. It's very interesting. You guys can go through that. More details you can go through that. That's nice. Good, Aditya Sharma. Thanks for sharing that.
Thank you, sir.
Yeah. Did I ask any other question in the previous class left unanswered? Yes. Okay, so I'll ask one more question this class and we will see if you guys can get an answer. All of you know tube tires and tubeless tires?
Yes, sir.
Yes, sir.
Tubeless tires can, they are also called as flat run tires. That means even if they get punctured, they can run for some distance without losing air.
Yes, sir.
Why?
Because of the thickness of the rubber, sir. Even though they said they are tubeless, they have air in them, sir. I mean,
That's
you
true.
can
It's
still
tubeless. It's not airless. It's air-filled tires still.
yes, sir.
They are only tubeless. They are not called airless tires. So there is air inside those tires, but how can they run even if there is a puncture in the tire?
I think they have a metal disc inside them that allows them to run for a certain distance after a
Metal?
puncture.
What is that?
Like a metal disc
No,
underneath it.
no. Okay, so this is quiz question for next class. Look at this, and if someone finds an answer, we'll discuss it. But remind me, one of you should remind me. I might forget. All right?
Sir, they have a strong skeleton-like thing, sir, which supports.
They do have a strong skeleton. I agree, but that's not the reason why they can
I
withstand.
mean, that can withstand, sir.
No.
Sir, in normal tires, when it's punctured, the air will release faster.
Why?
But in flat
I'm
tires, it
asking
won't.
you. I am asking you why. You are just explaining again the same thing that I told you. Why it is happening like that? Okay, think about it. All right. Thank you guys. So that's it for today. You go ahead. We'll meet in the next class.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.
See you.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.